Yes, am I audible? So we'll wait for 1 minute and then we can start the session, right? So that some more persons can join. And today's topic will be BJTs and OPAMPs, right? Bipolar junction transistor and operational amplifier. So today is the week 6 of the live session on the NPTEL course Introduction to Electrical Engineering. And in the week 6, we'll learn about these two instruments and we can just have concepts, revise the concepts on these two devices, the bipolar junction transistor and op-amps, which are very exclusively used in the electronic circuits for various reasons, maybe like as a switch or as an amplifier or to provide isolation and many other practical applications. So these two application devices are very useful for your knowledge of electronics. And we also covered the two-port networks in the previous week. So just these electronic equipments are having multiple terminals, right? Just for example, the BJT is a 3-terminal device. So the two-port network we told helps to actually minimize those 3-terminal devices into effectively as a 2-terminal device to convert them into to write the electrical circuit equations or electrical network equation for these two devices. And the op-amp also is a device which we actually use as an amplifier and to provide isolation also in some applications. So we'll see one by one those applications and learn about these two devices in today's session. But in the previous session, if you have any doubt, you can just ask me, or else we can just start with the session. So this is a brief description about my biography, and then we have these sessions every Tuesday, 7 to 9 p.m. And the next session will be on 11th. And these sessions are built to actually encourage you to ask doubts and be interactive, because these sessions are designed to solve problems and gain the concepts from them, as well as learn the things in an interactive manner, right? So I encourage discussion and also request you to stop me and ask any doubts if you get anything in between, right? Yes. So let me again reshare my screen. Yes. So what I was talking about is that we have these sessions every week from Tuesday from 7 to 9 p.m. and the link remains the same. You can just join using this Google Meet link when you are now. Same link, right? Which you are using now. And so if you have any doubts, you may stop me anywhere and ask me in between the sessions also. Okay. But because these sessions are meant to get your doubts clarified and also solve the problems and learn the concepts through the problem solving. So now we are at the week 6, as I told you, and in this week we will be actually focusing on the two devices, which are the bipolar junction transistor and the operational amplifier. So before starting these two devices, I just want to let you know two very important things, right? I think the screen is. Yes. So I want to ask you, I want you to be interactive, right? Otherwise, you will not learn anything. So we are the week 6 and two devices we told, the bipolar junction transistor and operational amplifier. Now, I just want to ask you why we use BJTs. What is the motivation that we use bipolar junction transistor? Yes. So BJT is bipolar junction transistor, right? Why bipolar? Can you tell? Yes. So can you tell why bipolar? Because there are majority as well as minority carrier. The current flow can happen and does happen because of the majority and minority carrier. That's why we have two kinds of charge carriers. That's why the name bipolar. And we have a junction. When I will speak about the device, we'll just explain. But you just for a moment, you just understand it is a kind of device where the flow of current happens due to both the majority and minority carrier devices. Both kind of carriers are there, and the device is constructed also like that, so that it bears both the device has both majority and minority carriers. In such a way, it is constructed. Now, why the name transistor? Anyone? Why the name transistor? So three words are there: bipolar, junction, transistor. So as you will see, it has the junctions, right? Junctions, and then we have two kinds of charge carriers. That's why bipolar junction. In different junctions, we have different kind of charge carriers. In a particular junction, wherever we name them in however manner, there are two kinds of charge carriers. Either they are majority or minority. So bipolar junction. But why the name transistor? So the name transistor comes from the motivation that we want to use this bipolar junction transistor in a way so that we can transfer the resistance from input to output, right? Transfer of resistance from input to output for same value of current. Now, one of you tell me, if I have the input port, we learned about two port networks in the previous week, right? And the output port, right? Input port and output port. And we have the current I. And here also, for example, this is the current I. Same current, right? Same current. Now, if I give I current at the input and I also see or want to have I current at the output, but with a different resistance, then can you tell me what will happen? If I tell you this is small r at the input and this is capital R at the output, then if I have the same current, which side the voltage will be more or the power will be more? Can you just unmute and tell? I want participation. So you can just unmute and speak, okay? That will help you. So if the current is same, but the resistance is small, then the power at input or the voltage at input will be small. Because I told you that at input side we have the lower resistance. Why and how we'll see. But just for the timing, imagine the bipolar junction transistor to be just a kind of two-port network. At the input, we have the input port, and the output, we have the output port. And what is the motivation? That we want the current to remain same, to push the same amount of current in a controlled manner. The current is same at input and output, but with different transfer of resistance. Now, by when I say that the current remains same at input and output, and the transfer of resistance takes place, what I actually say is the amplification of power takes place from the input to the output. And when the current remains same and the power is amplified, then the voltage also is amplified. So R pi and R naught, R pi or R in input resistance. Just simple, the device has an input terminal. Just for the time being, imagine. So if the input resistance is lesser than the output resistance, R0, but I remains same, then what we can say? P in is less than P0 or V in is less than V0. So power actually at the output is more. Power handle and the whole dipolar junction transistor, which is a nothing but a current operated device. This is a current operated device, right? Or in other words, just think this device as some kind of device which is activated whenever you inject some kind of current. So it is a current operated device, right? Just we'll see how it looks and why all. But this current operated device, this device will work when some current is given to it. But the input impedance or the input resistance of this bipolar junction transistor is very small. It is constructed in such a way. How? We'll see. And the output resistance of this device, which is known as the bipolar junction transistor, is significantly large. But it is designed in such a way that the input current and output current are same, almost same. So remember these things, very important, right? It is designed in its normal condition to operate in such a way that the input and output current are same. However, the transfer of resistance other of power is handled at the output, because for the same current you have the larger resistance at the output, so the power handle is more, or in other words the output voltage is also more. So what is output, what is input, we'll just now see. So the main motivation behind devising or fabricating this BJT is nothing but the transfer of resistance from output to input. In some kind of terms, we are talking about amplification, signal amplification, like in your audio amplifiers, or also some kind of switch application, because this bipolar junction transistor has 3 terminals. So it can be also used as a switch in cutoff region or as an amplifier in active region. Now what are they? We'll all to talk about all those things. But just for the timing, imagine the bipolar junction transistor as a current operated control device, which I am telling you from the starting, repeating multiple times. So current operated, okay, 3 terminal device with different input and output resistance, and designed to carry same current at output and input, almost same current. Now this is ideal case, it is almost, right, almost same current at to create such a device, because if you can create such a device, then you have two benefits. You have two benefits. How? You can kind of create some kind of device where it does not have the loading effect on the output. Now I can explain it in such a way that you have one device and you connect it to another device. Now you have one input. Now say for example this device creates some output for this device to operate. They are cascaded devices, and this first device, like your mobile charger, it is kind of charging your mobile, but from so you plugged in at the AC and then you get some DC. But do you want that when you charge the mobile, your output voltage vary because you're now loading the supply at the DC stage? So this is some kind of device. We don't want it. So in order to the voltage to not fluctuate very much, irrespective of change of loading condition, what can you tell me about the impedance, about the output impedance of this device? This device, its output impedance should be really high. Yes. Do you understand what I mean by that? Just unmute and speak up, okay? Did I tell correctly or I need some modification? In order for voltage to not vary across a particular port, irrespective of the current, what you can tell about the impedance? You just Thevenin, you apply Thevenin. You don't want this voltage to vary much, irrespective of the load current. What is your impedance? It should be large or it should be small? Yes? Easy
It should
question,
be
right?
large.
Just unmute and speak, okay? For a device which is intended to act as a restraint device towards loading effect, so that when I connect the load to some of its part, which I tell as the output, we don't want the current to change, or sorry, the voltage to change irrespective of the change in load. So what kind of impedance should it have? The source should have ideally. Like for example, you connect some load across your battery. You don't want the voltage across the load to change much, irrespective that the load is varying. Like in your toys, you don't want the voltage across the device to vary much, irrespective of the change in loading condition. So what is the impedance that the source should ideally have, so that the load does not create any loading effect and the voltage across the load does not vary much? What should be the impedance, this resistance?
No, sir.
It should be small or large? I want some answer, otherwise I will not proceed, because you need to have the fundamentals clear.
Sir, small,
Solving
sir.
any number of problems will not help, right? You need to understand the basics and then you will solve any number of problems. You need to understand the basics of BJT, right?
Sir, small value.
So what advantage it provides is that the output impedance of a BJT is high. How and all we'll see, but what advantage it will provide is that input impedance is very small. So input impedance very small, what kind of role it can play? Like for example, in this, the Thevenin equivalent. If the Thevenin equivalent and we have the internal impedance very small, then the voltage across load will not vary much irrespective of the change in current, because V supply minus whatever is the load current times R internal is nothing but load voltage. Now if R internal is very small, then irrespective of the variation in load current, our load voltage is almost equal to load supply.
Voltage drop is
Similarly,
less.
if a device is having a very low output impedance, then the voltage across the load will not vary much. Now, here in BJT, what we see? In BJT, what we see? So, these kind of devices which have a very high output impedance, what can they actually do?
Sir, transistor action take place, sir.
This was voltage, right?
Hello?
So, what can the device do, BJT? I want to hear some answers, some intuitive answers. Just speak up. Nothing to be worried about, right? You can be wrong, you can be right, but you can just explore. So which device has a very high output impedance? What kind of source? Yes? Is it a voltage source or a current source? I want to hear some answers now. If it is a current source at the output, it is intended to supply some current to the load. What will be its output impedance? It will be high or small, so that it can deliver actually the whole current to the load. If it is intended to deliver the whole current to the load, what shall be its output impedance?
High, sir, high.
Very high, right?
Yes.
So this should be very high. So such devices which are current operated devices, see, BJTs are actually current operated devices. You supply some current at the input, get some current at the output. Now if the output impedance is very high, the actual current does not get burdened by the load, and we can actually connect the load and we'll carry the same current by some biasing. We just see how it will happen. But what I meant to say is that it is possible to operate it as a current source, right? The BJT, it can be designed in such a way that you can operate it as a current source to supply a fixed amount of current, right? And it will not get perturbed. But it can be designed in such a way, right? In such a way. So BJTs are actually designed to carry some current and supply it to the load, like for example handling power at the output, larger power at the output, say signal amplification, noise cancellation, like your audio application, so that you can get boost of the audio from a very small signal. You can get the power amplifier, like a power amplifier or signal amplifier, signal level, because BJTs are not used in very high power application. So we are talking about signal level power application amplification, and obviously it amplifies the power, because for the same current in the input and output we have larger resistance, so output handles larger amount of power. That I already told you, output handles larger amount of power. So this BJT, how is it is constructed? So we got the motivation for the BJT. Now I will tell you how it works, right? So what is there, the BJT, how it is designed is a silicon bar. What is the idea, let us see, right? And divide it into three junctions. Same silicon bar, right? So you know the silicon, can I ask?
Sir, your audio is not clear.
What is the valency of silicon? I am not getting any answers from any one of you. Can anyone just unmute and tell? What is the valency of silicon? What is the atomic? Just part to worry, right? You can be right, you can be wrong. What is the thing? No worries, right?
Sir, valency
Yes,
is 4, sir. 4.
correct. Valency is 4 because the atomic number is 14. And
Yes,
by the
sir.
simple rule, as you have learned, you can see that the structure has 4 valence electrons. So in silicon bars, whatever you get, and you manufacture those silicon wafers, you do what? You dope them with different kind of elements like the boron or indium or phosphorus. You have different elements which are just beside, ahead or after in the atomic table, right? So we have the silicons. So and the silicons are like this. So we have 4 electrons in the lattice of one silicon atom, and then we have similar structure, right? And they all form covalent bonds, which are very strong metallic bonds, right? Similar structure, right? And they form the bonds, very strong bonds. To get actually inert, right? Their tendency to is to get inert. So they will form the bonds. Now if you introduce, like with other atom, I hope you understand what I am telling, right? This was the whole purpose. And then now you injected some different kind of, which the valency of boron. Boron is another element which is very extensively used to create the p-type elements, right? What the p-type elements mean? That they have extra holes which has affinity towards electron. The electron seeking affinity, right? Or electron affinity, you can tell. So boron has 3 valence electrons. Now it sits beside one silicon, and there is silicon on top also. So it will start forming bonds with the other silicons. But here it cannot do anything. So what we tell, if some electron is given or it has accepted one electron from somewhere, either from an external device or somewhere externally, right? Then this lattice will be forming another bond. It always has some electron affinity. It's like a positive charge, right? It seeks some negative charge. But please understand, it is electrically neutral still. Hope you understand what I am trying to tell. Although it has a hole in the p-type material, p-type doping, they are always electrically neutral, right? It has affinity to accept one electron to form the lattice and bonds, but before accepting the electron, it is still electrically neutral. Although it has a electron affinity to accept some electron, it is electrically neutral still. But after accepting the electron, it will have some charges, extra charges. So that is the whole purpose, please remember. So boron is used for p-type doping. And p-type doping, what is the majority of the carriers? What is the majority? Holes. Like positive charge. But holes never move. Actually, you can understand holes never move, right? The electrons will move, and we say that the holes move in a direction opposite to the movement of the electrons. And the direction opposite to the flow of electron constitutes the flow of current. These two fundamentals always you should remember. Now, similarly, if we dope with phosphorus, what is the valency? 15, right? Phosphorus is 15 atomic number. So what is the valency? 5. So as you can understand, if I insert a phosphorus, it has forming bonds with other silicons, as I did. Still it has one electron extra, which will be free to conduct, free charge carrier we say. So these kind of use are used for n-type doping, which are having actual electrons or free electrons for carrying charges. So for n-type doping, you have electrons as majority carriers, and for p-type doping, you have holes as majority carriers. Now let us see the construction, how they are done. So let us, for example, assume we have a silicon wafer, and in one part of the silicon wafer, we heavy doping is indicated by plus. Don't get confused with charge. This plus indicates heavily doped. Let us create a section, not a very large section, but a relatively smaller section. This is a smaller section, but very heavily doped. Let us create. How? By injecting phosphorus. Let us say n-type dope, heavily doped, okay, but a relatively smaller section. And this base, I will draw it correctly. This, let us create a narrow section and lightly doped, right? Relatively, moderately, I can say, moderately doped. P. That's why I did not place any plus or minus sign, right? Which indicates it is moderately doped, but thin region, not much. This is thin, right? And one is actually a bigger portion of the wafer, which is very lightly doped. And I created such a device, right? Such an arrangement, I can tell. And I named this terminal as the emitter, maybe, which I denote by E. Now I will denote the 3 terminals of the BJT and will name them as emitter, base, and collector.
Sir, hello.
Yes.
Sir, I think base is lightly doped, sir. Collector
Base is
moderately doped.
correct. Base is also lightly doped, and collector is also lightly doped. Actually, see, light, moderate are all. See, base will be lightly doped because it is a very thin region. But see the density. What I am telling, you are correct. Both are actually lightly doped, and just now you will understand what I am trying to tell. But what I am telling is, base is a very narrow region, not much like the collector.
Yes, sir.
So collector, even it is moderately doped, but a larger area because it has to handle a lot of power at the output, right? Power amplification is done. So I tell both as lightly, right? But you are correct. It is moderately doped, yes. And base is lightly doped. Correct, very correct. But in this, that's why I am telling thin, right? Moderately doped. Thin, that's why the density is relatively larger, but the number of carriers are still small. Very low carriers, right? Very low carriers. Low number of holes compared to the other two. Just now you'll see what I'm talking about. Now you have this device, right? N, relatively small p, and then n. Now a phenomenon will happen once you construct such a device. Immediately one phenomenon will start. What phenomenon will start? Let us understand with a different color. Now you heard about charge recombination and creation of space charge. What is that? I will make you understand. Whenever you have such, it is like kind of diode, right? 2 diodes sitting one by one, right? And whenever such junctions are formed, right, a phenomenon will start happening. What phenomenon will start happening? Can anyone tell me what is the majority carrier here? These are electrons, right? It has free electrons. And this region has a lot of free electrons. And this region has some holes, right? But few holes.
In
So
P
what will
region,
happen?
majority carriers are holes, minority carriers electrons.
Which one?
In P region,
Majority carrier holes,
holes.
obviously. Because we doped with the holes, right? But doped with the p-type elements, right? And that's why they have formed holes. They have affinity to seek electron. Now what will happen? Since it has affinity to seek electron, the recombination will start, because adjacently it gets electrons. So some electrons tend to move from n to p, n to p, like that, this. And what will
Diffusion
it?
will start, sir. Diffusion.
Diffusion will start. So what will happen? Or recombination. Actually, charge recombination I am telling, but still it is electrically neutral. Please understand. Only the reallocation is happening, right? The total element is still electrically neutral. Total element, right? But the charge from here it goes there. Only process. Then what will happen? Then you have some portion internally, you have negative and positive, right? If electron jumps from this side to this side, we can imagine that holes jump from this side to this side, just like that, you can imagine. And that's why a reverse electric field region will be created, which opposes further flow of electrons from this side to this side. So the process itself will retard with time. Otherwise, all the N-type material will go to the P-type and everything will be gone. Such things don't happen because nature itself opposes by creation of internal electric field. Such that internal electric field which is developed in that region or the depletion layer, that does not have any free charge carrier, right? So it opposes the flow of the such free charge carrier till the time some external electric field is applied to make such flow possible, right? So what we do, we need to have some flow, so we forward bias this NP junction, or the emitter base junction is forward bias. Once we forward bias, because we have doped it heavily, majority of the charge carriers, which is here the electrons in the N, will jump and will cross the barrier, because the field, external electric field to the battery, what you call as the forcing field, is more than the depletion, and slightly it will reduce, and the charge carriers will be crossing, actually crossing into the region. But as soon as the charge carriers cross the barrier, enter into the P, the P has affinity towards electron, but it is lightly though. Let's say 10, and it has 100. So what will happen? From 100, 10 will go and combine. And remaining 90, these are electrons. Current is flowing in other direction. Electrons are flowing in N to P to N, like this. So remaining, say 10, but actually 10 is not lost, it's say 5 is lost. Very less, because as you correctly told, the base is very lightly doped and this is of the thin region. So how many will combine? Maybe 5, 6, like that, for example. So remaining 95 goes to the N. So how it goes? Because we have created another arrangement. Because these are electrons, we connected here positive plate and reverse biased it, like this. So we collect these electrons, these 95 and this 10, this 95 returns here, and also this 5 and this 95. Sorry, this 100, right? So electrically the complete system still remains neutral. The battery is doing the magic and helping it to maintain its original doping characteristics at the end of one cycle process. So whatever charge entered, it recombined, it was forced to go out, such that eventually nothing is changed. That's why the device remains the device, right? It does not recombine and the characteristics is not lost after the forcing is taken away. So the NPN remains the NPN because of the battery. Whatever we are doing, we are only allowing the flow of current from a very low resistive zone to a very high resistive zone. This is the magic that is happening. And there is a biasing. Because of the biasing, the power is amplified. So what is the magic? Power is never amplified without external source, right? The magic is happening because of the battery, VCC. And the forcing function was the base. So the base voltage was VBE or something they call VBE, base emitter voltage. That was actually starting, initiation of the process. Now the help was done by the VCC or the biasing to seek the charge carriers and actually make it happen such that at the input current, the emitter current was actually almost equal to the collector current. The current in the collector, we tell it collector current. But due to the reverse bias, there is some leakage current due to the flow of the minority carrier devices, or the reverse small leakage current is there. But that is very low, and actual current is led in the I can say in the collector from this emitter junction, which was highly doped. So the flow of currents which was actually happening is due to the highly doped emitter junction. All these 95 electrons work from there. But you can understand, since we have collected the positive plates here, what will happen? We are trying to reverse bias, right? So what will it do? The minority carriers actually. So reverse bias does what? Reverse bias actually allows the flow of minority carrier device. Forward bias actually allows the flow of majority carrier device in a simple language. What is the majority carrier device? In the collector, electron. But we are doing reverse bias. If there are some holes, that will be actually repelled. And that leads to a very small amount of reverse saturation current. But that is negligible because it has very less holes. Mostly it is having electrons. And the electrons of the from entering from the base to the collector junction are attracted, and the flow of current is actually possible. Now this arrangement helps to amplify at the power stage, at the output. And this kind of arrangement is possible using very carefully selected and designed emitter, base and collector junction. This magic, what you are seeing, is happening only because the base was thin and lightly doped, collector was moderately doped, the larger number of relatively larger than the base, but the emitter was very heavily doped. That's why this kind of working is possible. So I hope this is clear, right? How the current almost remains the same. So always remember that the biasing voltage VC than VE, and the current IC is almost equal to IE for a normal operation of the BJT. And the IV, which is the base current, as you can understand that the base is very lightly doped, and recombination, the base current, why it happens? 5. Because the recombination of the electrons trying to enter from N to P and then trying to go from P to N into the collector. So there a small recombination happens, and that is again supplied by the battery. So that small amount of current is the base current, which is actually forming the link from the one of the junction to another junction. It is a linking part, the base part. So that linking is also requiring some small amount of voltage to initiate the process. I told you, to initiate the electric field and to allow the flow of charge, push the electrons from emitter to base, and then the collector will help to seek the charges. But there the small recombination was done, and small recombination leads to the current, which is the base current, the activating current. But that was very small, so it can be assumed to be 0. Why? Because the base has very less number of charge carriers, free charge carriers, which in this case is the holes. So that's why the base generally in many problems you will see at the normal operation. In normal operation of BJT, we can assume that the base is not having very high amount of current, but the collector and emitter almost bears the same amount of current. This can be assumed, but never assume. If anything is said, then you need to calculate the base current also. Base current will be in order of microamperes, right? But still you need to include that in the calculation. You cannot just assume 0. If things are said, you need to consider that in the problem. So we'll just see how to tackle those kind of problems. But hope you understand the working, right, of the BJT. So construction wise, I told you, construction wise also the BJT is done how? By taking a wafer and then you actually follow you have the silicon wafer and actually you dope it lightly to create the larger collector junction, and then you have silicon oxide layers to create the junction to the etching process, and then you again kind of create a zone to create the to again dope with another material which will form the base, and again you form the etching process, you take the terminals out from here, again you do the selective etching process, and within that you again form the n layer which is highly doped. Now this was the forming the maximum area or the collector lead which will actually be thick and placed with a dot to identify, right? To create a actually there is the larger lead area because of the larger power dissipation. It is also thicker, right? Thicker and lightly doped. Thicker and lightly doped. And the base was moderately doped or very lightly doped, the thin region, right? And then again we come the N. Now this will form the emitter, this will form the base, and this will form the collector. This is a simple construction process, and the techniques are different. Many advanced techniques are there, how you create them. But the motivation is that we have to create three differently doped as well as different thickness regions. And if we interchange maybe emitter and collector, the transistor may burn out, right? Because you need to understand that the emitter base is forward biased. Now it is designed to bear a particular amount of current. Now if you interchange, then what will you do? You may lose the device functionality, or in other words, if the emitter is provided a higher voltage, base emitter voltage is generally lower. So if you think it to be the collector and place a larger voltage, then it may damage the base emitter junction because it has lot of charge carriers. And if you force the electric field to be so strong and it is forward biased, then the current will be too high and it may damage the device. In other words, if you do not the device also, placing a smaller amount of voltage at the collector, which is the output, thinking it to be as the emitter, because you forgot, you interchanged emitter and collector. So if you place, actually VC is more than VB, get it. Now interchanging the two, I told you, emitter place to only initiate the process, and then collector will seek those charge carriers, those high number of charge carriers. But if you interchange, then you would place a larger voltage in the emitter base bias, which will damage the junction. In other words, if you also do not damage, may think it you do not damage, then you have a lower voltage at the output, which will not amplify. The main purpose of the BJT, which is amplification, will be lost. Because now, in a larger zone, you are actually biasing it with a lower voltage, which will not lead to higher, or it will not lead to the transfer of the total number of carriers. So you will lose the device functionality and will be under efficient. Its performance, so performance degraded if you interchange leads. So never interchange leads. This is very important, right? So, and the characteristics of BJT are very interesting. Now see, just think, as we have understood the construction, we know that the base junction is actually the activation junction. Unless and until you activate that by the electric field, external battery or external source, you will not get that function. So if you see the characteristics, the input characteristics, which is from the base, for a base emitter, common emitter, if you think the emitter, call the vector, the base, and the emitter. And this is a NPN type, because I know that current flows from P to N in a NPN. If I dope as NPN, I know that current flows from base to emitter, right? I also showed you that current will flow from base to emitter, right? So we need to forward bias the base emitter junction in a common emitter configuration, which is the normal become a normal operation of the BJT. We use it extensively and with actually reverse bias the voltage. So we actually place a positive voltage for the currents to flow. Current will flow in this direction from top to bottom. But actually you understand for NPN, the electrons are actually the carriers which flow in the opposite direction, just as we saw the operation. But the current flows from top to bottom because the electrons flow upwards. And also similarly, the current flows from P to N, but the electrons flow from N to P. The emitter, highly doped emitter, N to P. Electron flow, so the current flows from this direction. So this arrow actually denotes the type of BJT. So you can easily identify that PN and the N. So NPN. And this arrow indicates the flow of direction of current, not the charge carrier. Now, as you understand, for a common emitter means the voltage across the emitter is common for both the input and output, as you can understand. So if I increase VCE, that means I am increasing the reverse bias voltage. So first you need to understand that I need a slight amount of voltage at the input, which is the VBE. VBE means the input voltage, input activation biasing voltage, which you apply across the input to create the activation, to force the carriers from emitter to base. And once the electrons are forced from emitter to base, the current flows from base to emitter. Simple configuration. But for that also you need a small amount of voltage, maybe 0.3, 0.4 voltage. And after that, you can attain the base current by increase the base current basically. Place a small amount of resistor and you can control the base current. What advantage the controlling the base current gives? Yes. For a different voltage applied across the base, you can control the base current, because controlling the base current means controlling the flow rate of the charges. Now obviously that can be done with the help of a controlled resistor, that is a different resistor. For a particular application you can use a fixed amount of resistor and a very wisely chosen voltage VBE, because the base voltage which is actually impressed through the collector, through the base terminal of the transistor, is very important. If it is very high, then it may damage the device. So that's why we need a resistor, base resistor we call it. Now the base voltage, which is the base lead voltage of here, it needs to be such that it allows the base current to flow. And actually we can see in the characteristics also that if the base current is high, then it can allow more current to flow, more collector current to flow. And that is very intuitional, because as you can understand, if the base current is high means what? If the more charge carriers are entering into the base, that means more charge carriers are also forced from the emitter. That will lead to higher number of charge carriers at the collector, just based on the operation of the transistor. But that also has a limit. It should not exceed, otherwise it will burn that zone. If more charge carriers are forced to actually go, it may lead to some punch through and may damage the junction. So that also needs to be very carefully selected. And once you can have the attaining capability, you can also increase VCE. Now what increasing VCE will actually do? Increasing the VCE, you can see, will indirectly reverse bias the base emitter junction. How? Because this collector voltage is there, and if you apply KVL across this loop, because there is also one biasing region, right? Because actually we don't apply to separate sources. What we do, we do what? We have the NPN transistor, we apply a common this source and use to different values resistances. Now this voltage will be obviously small, so you use a larger resistor and you apply, and this is common. So this is how it is done. So what happens if you increase VCE? What happens if you increase VCE? This voltage increases. If this voltage increases at this node, then this, what happens? Yes, I want to hear some answer. If VCE increases, what happens? Please answer. if VCE increases, you are actually providing at the output a good lead which is highly charged to seek those electrons faster. So what will happen to the recombination that was happening at the junction? What was happening at the junction? NPN. What you applied? You did what? You forward biased and you reverse biased. Now you increased this voltage. Now it will seek the electrons faster, right? Without giving it time to combine in the hole. So what will happen to the hole current or the base current? It will reduce. So see, effectively what happens, the base region actually shrinks due to the application of reverse bias zone, effective base region. So that's why, in other words, the recombination process at the base is not that much, because you are charge carriers to quickly flow into this region. So the recombination is not there, much recombination. So that will reduce the base current. So see,
Reduce
when
the
DC
effective
is a
base
base,
width, sir.
yes, that will reduce the effective base. In other words, people say it in different languages or different explanation, but just the way I told you, that the charge carriers are very much forced due to the applied electric field externally at the output, so that recombination process lowers. And if recombination process lowers, effectively the base width is also lowered, right? So that's why increasing VCE, you can see for a given VBE, if you apply higher VCE, then it will lower the base current. So you see, the base current for a lower VCE was higher than that at a higher VCE. So hope this is the input characteristic, which is very much intuitive and very much aligned to what we have discussed. If you understand the operation, you will not face difficulty in understanding why this actually action happened, why it happened. So this is known as the input characteristics of a BJT, right? And you can understand, after the threshold, you can push any amount of base current depending on the chosen value of base resistance and the applied VBE. So this is the very intuitive basic characteristics. Now, if you see the output characteristics, I told you output impedance is very high for a BJT in operating in normal operating mode. So you see the output characteristics, what can you judge is that initially for a, now the imagine, keep that structure in your mind, that it is the NPN and this is collector, this is base, this is emitter, and what we do, we choose a source, VCC we call it, but we have a resistance, because to protect the device or some biasing action we need to provide a particular VC, and similarly we have a resistance here, RB, and this is RC, and this is RE, okay, and this is ground. So this is this. There is a resistance here. This is a VBE. Sorry, VB, yes, and E. So this is the VBE. Because VBE means what, you understand? Don't get confused, okay? So VBE means the voltage between the base and emitter leads. Where are they? They are here. But since there are resistances, we need to appropriately apply the voltages at the outer leads. Now, generally, you can see that VBE don't change much, because it is a very small region compared to the collector and behaves like a diode. Its drop is very much fixed to 0.7 volts, just like a diode voltage drop, because it is forward biased, right? So once it is forward biased, since it is a diode, the junction drop is very small once it is forward biased, behaving like a link. So the voltage drop, irrespective of the value of IB or IE or IC, the VBE actual voltage between the base and emitter junction is almost fixed. because it is forward biased. And in forward bias, the only drop voltage is the forward bias drop. In the diode also the PN junction drop around 0.7 volts. So 0.5 to 0.7 volts. So please keep that in mind. Now what we see, now you don't touch the input. Now let's play with the output. You increase VCE. What I told you, increasing VCE will do what? It will pull more charge carrier. In other words, it will push more current, allow more current. So that is what is happening. You see, initially you increased VCE and IC increased. But after that, increasing VCE does not increase much. It is increasing, still increasing. The curves are not properly flat, but also not straight. Slight increase is there. Why you know? Just like your magnetic dipole. Once all dipoles are aligned, magnetic saturation happens. Similarly, when the forcing function crosses a particular threshold, like for example VCE positive lead to seek the electrons, all the electrons from the coming from the base is attained at the collector, then nothing can exceed them. And we are not changing VBE, but we are increasing VCE. So keeping VBE or input constant for a constant forward bias voltage or current, the flow of electrons is almost very much decided. Now if I increase the output collector voltage, then they will be slightly increased because of the whole recombination process reducing a bit due to the applied more electric field at the output. But how much? It will be not much. So the electrons will, after a time, it will not matter much. So, and it may damage the device also, because I told you all these junctions are very carefully designed and the voltage across those junctions should not exceed. Otherwise, breakdown will happen. Device may break down. Its voltage blocking capability or reverse bias voltage applied it can break down the device. So that is very important that you do not damage the device. But as you can understand, slightly it will increase. And if you extrapolate, then some voltage you will get for which the collector current will become zero. Obviously, if you apply opposite voltage, the collector current will cease to reduce. That voltage is known as the early voltage. Just technical terms, and they will have some different early voltage, and you average them and find that this early voltage is around 100 volts for a typical BJT. And then that is the active region, and then if you apply something other than positive VCE, then it is just called as cutoff. Sorry, saturation, right? So saturation, anyone understands what it is actually happening? Yes. Saturation and cutoff. So cutoff you understand, I think. Cutoff means that no current it is behaving as a switch. So when it will happen? That when you just off the base. So base current was this. Then you get some in output characteristics. Base current increased. You see IC increased, as I told you, because base current itself leads to born the IC is born from where? From the base. The IC current is only because of the base, but also due to the output forcing function, which is VCE. But the base was actually the starting reason for IC to be born. So as you increase IB or the input forcing function, charge carrier increases, and that will lead to higher IC for sure. And if you see with respect to VCE also, increasing VCE also slightly increases IC. But if you seize the IB, if you completely remove IB, then it will be a cutoff where IB is 0, IC is 0. IB is the control handle at the input. You turn off the device, then the IC also will be 0. It behaves as a switch. Just due to the intuitive reasons I told you. How can IC be there if there is no IB? Because the whole device action is stopped. So that is the cutoff. And active region I told you. Then what is the saturation region? This saturation region is actually what? This saturation region is a region where the device, where the VCE is something other than positive. Now, if it is so, then it will lead to very small amount of current, right? It will almost cease to zero. So that is a zone which we call that the device is saturated, right? So that is the saturation region where the VCE is anything other than positive. It may be zero, it may be negative. So that is a saturation zone. And that zone operation in the saturation zone may also damage your device because it is not a normal zone of operation, right? So device is actually intended to operate in this active region. So this is how the output and input characteristics are designed or they are for the BJT. So can you tell me quickly the BJT, if I draw like this is a current operated device, and if I draw the switching characteristics, how will it be? If this is V, this is I, in which directions the current can be and which directions the voltage can be? Can I apply voltage anything other than plus VCC and relatively 0 and some VB? So can it block any voltage other than plus positive VCE? No, right? So voltage always needs to be in the positive side. If it is opposite, device may break down. So only positive forward voltage blocking is allowed. That if you seize the base, then also it can block the positive voltage. Otherwise, device will fail. And only one direction the current will be there. Current flow only in one direction. So current also, when the device is on, then current also flows in positive direction, which I draw by this arrow. Reverse direction current cannot flow, right? If there is an anti-parallel diode, then what will happen? So for the time being, don't assume any anti-parallel diode. But if there is any anti-parallel diode, then what will happen? Yes, tell me. Can it block forward voltage? Yes. Can it block reverse voltage? Answer is no, because still the device will be damaged. Diode will not diode will conduct, that is different thing, but the device will be damaged. So voltage always needs to be applied, positive voltage here, negative voltage. Otherwise, device will break down. This device will not perform correctly. But the current can be in both directions due to the diode. When the device is on, the current can be in both directions. So current can be in both directions, forward and reverse, both. So these are some of the characteristics, as you can understand. So some important definition, as I told you, I already told you about the common emitter, that what is the input IB, which is the base current, and output is IC. And input voltage between base and emitter, these are all known. And the current gain. Current gain is nothing but output by input. Output current is what for a common emitter mode? Output current is IC, input current is IB, and this is greater than 1. Why I told you? So as you can understand, base current is very small, right? And collector current is very high, and IC almost equal to IE in a common emitter configuration. Base current is very negligible. So IC by IB is relatively very high for such configuration. So that's why they call it current amplification. And current gain is high. And voltage gain is high because I told you same current times resistance. Now output resistance is high. That's why voltage at output is high. So voltage amplification is there in common emitter mode. And then phase change is 180 degree, and application is actually, it is, I told you, just signal amplification, right? So that is what we have learned. And similarly, its dual versions exist, but they are not very extensively used in amplification stage. This common emitter much used in, but the role or the zone of operation of the device will be governed by the choice of biasing resistances other than the biasing voltages. So both the mode of operation, what mode of operation you select, declared by the application of specific voltages at the emitter base and collector leads, and alongside the choice of the resistances, the biasing resistances and the biasing voltage values, equivalently decide the zone of operation as well as the mode of operation of the BJT. Otherwise, you don't have those amplification regions. These amplification regions also are needs to be properly selected by proper choice of RB, RC, and RE. Just we'll see some numericals and you will understand. So I have just, for your reference, I have just placed the important terms which you already know: the current gain beta, the transconductance. When you learn in the analog electronics also, the transconductance, which is nothing but I have written the definition. It is nothing but the collector current by the base emitter voltage. But they coined the name because these terms are very extensively used in the small signal model. So once you understand the operation of the maybe BJT, then in analog electronics you will learn about their small signal behavior, where you will develop the small signal model. And in small signal model, these terms IC by VBE, this becomes very big. So instead of writing them several times, we use notations. The transconductance or the output impedance R naught, input resistance R pi, and their order of magnitudes to give you an idea how they actually look. So these are all written in a place. That's why you get the reference from here, right? That's why I wrote them. And basic relationship like the how the collector current depends on the, when I not have any kind of collector emitter voltage and I want to see how the collector current depends on the base emitter voltage, then you know it will increase with the base emitter voltage. Very intuitive. But that is in a consideration that still VCE not applied. But as you understand, as you also apply VCE, it will not have very significant role on IC because the initiation is already done by the input terminal, which is VBE. It only helps to push the charge carriers to the output. So yes, after a very significant, after a small increment in VC, from there onwards, it does not have a very big impact on the IC because of the effect of saturation. Now, effect of saturation means all the carriers are aligned and want to go there. That's why the current does not contribute, and current significantly does not increase in amplitude because they are already flowing for a given VBE and IB. That's why it significantly depends on VBE or base current. Base current, if it increase, more carriers will flow. That's why IC will obviously be higher because IC almost equal to IE. But still, you can understand VCE also has a role on IC because slight increase in VCE will help in the movement, but not much because they're already aligned. That's why if you want to, and these are all the how applying the VBE will actually just basically diode equations with some modifications, right? They're all already diode junctions, PN junctions, so we'll follow them. And when VCE was 0, we know the formula, and the role or the of VCE on IC still have a linear role because in the linear region you can see some increment, but very small because the dependence on VBE and VC can be coined included in the IC, and it has a more dependence on VBE and lesser dependence on VCE, as you can understand, because of the very intuitive reasons that I already explained. That basically VBE will drive IE and IE is almost equal to IC. IE is actually the reason for flow of IC, and VC only helps the flow of those electrons, and that's why no significant increment in the charge carriers for a given value of VBE, right? Now, with all these knowledges, I think you can solve the basic problems on BJT, right? In the introduction to electrical engineering level, the basic problems on BJT were now equipped to solve with this knowledge and the working of BJT. So the first problem is on your screen, and I want you to try these problems, and then we'll have a discussion. So first, I want you to take some time and just try the problem. So first problem is on your screen, and just see it and try. Okay, I'll keep a pen and paper with you and ask if you have any doubts, right? So beta you already know, right? It is a current gain. And this is IB, and this is NPN, and this is IE. So beta is what? Output current by input current. Now you try. Beta is given as 75. VC is given to be 9 volts. Then find RB by RC. It is asked. Try. Just tell me how will you solve. Are you with me?
Sir, IC equal to 15 minus 9 volts divided by RC.
Okay. Then you don't know yet. Yes. I know. Also, you TB. Now take RB into role. Do you know VBE? Can you tell what will be IB? Can you see my screen?
Yes, sir.
Okay. So just can you tell me what will be IB?
IB.
Yes, what will be IB? Because I know I need to have RB by RC, right? RC you told me some value. If you can somehow develop a relation with RB, then I can divide and know the current gain, right? Then I can find RB by RC.
Sir, IC equal to 75 into IB.
Okay, but how can it help? You need to have another relation, right?
Yeah, beta equal to IC by IB equal to 75, sir.
Then what will it happen?
From this equation, IC equal to 75 into IB.
Then how will it help?
Substituting here above equation, replace IC in place of IC 75 into IB.
Yes, correct. IB I can replace, okay. But what equation can you form with IB? So this is the base junction, right? This is the collector junction. This is the emitter junction. So what is the voltage? Base emitter voltage I told you is always
0.7 volts.
Remember this. This helps.
IB equal to
Then IB equal to
0.7 minus 9 divided by RB.
so let us take it in this direction because IB will flow from into the right. So what direction can I select? Yes.
9 minus 0.7 divided by RB.
Yeah, so P to N, right? So IC is equal to IB plus IE, right? And then VB is 0.7. So how can I write IB? IB equal to 9 minus 0.7 divided by RB. So this voltage is 0.7 and this voltage is 9, right? So 9 minus 0.7 by RB. This is IB. And IC is 15 minus 9. What is 9 minus 0.7? 8.3 by RB. And what is IC? 6 by RC. So what you can do, you know IC by IB, it is 75, and IC is also 6 by RC, and IB is 8.3 by RB. So we know 75 equal to 6 by RC into RB by 8.3. So what is RB by RC? Right. Just calculate.
Sir, 103.75.
Huh. Correct. So approximately it will come like this. Okay. So what I did, I wanted to find a relation of IB and IC involving RB and RC. Now since I know IB by IC, sorry, IC by IB, I can easily find out that. Any doubt, you can just let me know. Yes. Even doubt. Am I audible? Hello.
Not audible, sir.
Now I'm audible, right?
You are audible, sir.
Okay, sorry for the delay. Just we'll share the screen and you can see everything. Okay. So this was the problem, right? Yes, this is the problem that is popping up on your screen right now. So it has given you beta as 30, input voltage as 5 volts. Here, right? This is 5 volts. And this is the VCC, what we call the biasing voltage at the collector. My voice is clear, right?
Clear, sir. Clear.
It asks you to show that the transistor is operating in active mode. So what happens in active mode? Base emitter junction is forward biased and collector
Collector
emitter is
junction
reverse
reverse
biased,
bias.
right? So you have to show VC to be greater than 0 and VB to be greater than 0. Agreed? If these two are satisfied, then obviously normal operation in the active region is attained. Can you solve it and check? So VB is 0.7, you can assume. So you just show that VC is greater than 0. So collector based junction should be reverse bias means VCB should also be greater than 0. Actually, collector based junction should be reverse bias, right? Means VCB should be greater than 0 also. So can you show this VCB? This is B, this is C. So show that the difference of these two voltages are positive. This you need to check actually. Can you do? So what is VB? This voltage. VI. Yes. What is VB?
VI minus 15 into IB.
VI minus 15. Why 15?
15 sir, 15 voltage drop. 15 kilo ohm resistor voltage drop.
So how will you write VI minus? No. This cannot be written as IB. This is not IB. This is IB. Whatever is going into the base terminal. This is not the base terminal. So these two currents are not same. This current is coming like this. Some part is going like this. And then some part is going into the base. But since this voltage is 0 volts and this voltage is 0.7 volts, so you can write VB as 0.7 volt. From here, what can you know is the current that is actually entering into the base. So try to find the current that is entering into the base from the knowledge that VB is 0.7 volts, and since it is forward bias, you can actually claim that this voltage is 0.7 volts, and once this voltage is known, you can calculate this current from the knowledge of VI. So try to calculate this current IB.
0.407 milliamps.
How you calculate it? First you explain. Don't jump into the answer.
Okay,
so what
sir.
is IB?
Sir, here
So what is IB?
Sir, 5 volts, VI minus 0.7. 5 minus 0.7 divided by 15 kilo ohm.
Yes, but that is not IB. Please understand. This current minus the current flowing here, which is 0.7 minus -12 divided by.
Yes, sir.
$100K. This current is IB because the current was flowing from here to here. Yes, please. Someone has a doubt. I think you can unmute and tell. Someone raised hand.
Understood, sir.
So what I am telling, just for the sake of your understanding, there was a voltage at the input, but this terminal was not the base, and neither was this current the base current. What I mean as the base current or the base terminal is where the transistor is there. But before that, two external resistances are connected and are grounded with -12 volts. But I know that since the NPN is operating in the active zone, if I assume and want to prove, then if VBE is forward biased, as I told you, and once VBE is forward biased, it is 0.7 volts drop. So if VE is 0 volts, VB is 0.7. If VB is 0.7 and VI is 5 volts, by using network theory, we can just conclude or just can derive what is this current, but not directly. How? This current we can calculate by VI minus 0.7 by 15. But this current is not base current. This current minus this current. This current, how can you calculate the current going down? Is nothing but 0.7 minus 12 volts by 100 k. Which is also a small current. And the difference gives us the base current. So calculate what is it. Vi is 5. So calculate what is IB. Please calculate, okay?
0.153 milliamps.
0.1.3 means?
0.153 milliamps.
Okay, just let me check. 5 minus 0.7. You please do again and just check. Recheck, okay? Minus, what are we doing? 12 plus 0.7. So I can write 12.7 divided by 100. 1, 2, 3. But I am getting some different answers.
How much, sir?
0.28 around I am getting. Let me again check.
Sir, I told
Yes.
total IB value, sir. I told.
This is 15 kilo, right? Sorry.
15 kilo. 0.28. 5 minus 0.7 divided by 15. 0.28 milliamps.
Or what you can do, everything you can calculate in milli, right? Everything calculate in milli. Forget about the kilo, right? So what you can write, 5 minus 0.7 divided by 15 minus your 12.7 divided by 100. But this answer is in 0.159 milliamps.
Yes, sir.
Or 0.16, right? So as you can understand, the base current is a really small current. So now calculate IC. Easy. IC is beta IB. And IB is nothing but beta means 30 from here. And what is IB? IB is 0.16 milliampere. So what is it coming IC? Please tell me in milliampere. So 30 times amplification you are getting. And the answer is 4.8 milliamps, right? Now can you calculate? You know IC? VCC minus IC times 2.2 K. IC is 4.8 milli. Milli and kilo gets cancelled. And VCC is 12. So VC is what? VC means the voltage at the lead of the transistor. So VC is what? 12 minus 4.8 into 2.2. So can calculate VC. VC means this voltage at the lead of the transistor. So calculate VC. 12 minus 4.8 into 2.2.
1.44 volts.
So now can you claim VCB? What is VCB?
VCB. VC minus.
That is what we need to check.
1.44 minus 0.7.
Is it greater than 0? Yes.
Yes, sir.
That means the VCB, voltage impressed across collector base, is positive, which means the collector base is reverse biased because VC is higher and this is a NPN transistor.
Sir, VCB
Negative has higher voltage.
VCB,
So VCB coming
0.74
positive.
volts.
Correct. That means coming positive means that it is reverse biasing the collector base junction. So collector base junction reverse biased as VCB greater than 0 implies that the operation is in active mode. Basically, active mode operation is that only. So see the next problem. So here also, as you can understand, VBE is 0.7, right? And they have already asked you to consider IC and IE to be almost same. And current gain you take beta IE. Can you calculate V0 quickly? V0 is this voltage. quickly. By apply KVL,
Yes, sir.
then this loop. Then what is it? 10 minus
10
5
minus
kilo.
5k ohm into I, IB, IB
Correct.
minus
Then
0.7
correct. Minus 150 into IE
IC.
is 0. Now, what is IB? IB and IC has a relation like this.
Sir, IB means 10 minus 0.7 by 5 kilo ohm IB.
Correct.
Into beta. IC is 148.8 milliamps.
10 minus, no, 10 minus 0.7 by 5, what you are telling is IB, agreed. But you are using the KVL loop, right? We have already taken into consideration 10 minus
Okay.
0.7. So again, you cannot use it in this equation. Then everything will come to be 0. Because you are already applying the KVL, right? So 10 minus 0. Whatever you are telling, 10 minus 5 into IB, minus 0.7, minus this is 0. Then again, writing IB to be 10 minus 0.7 by 5. Hope you understand. We'll cancel everything. Because you have included it in this equation. Now use this equation. Yes. So how will you use? Please think and answer. So beta is 80, right? So 10 minus 0.7 means 9.3 is 5k into IB plus 150 into IE. So what is IB? IB is nothing but
IC.
no. IB and IC, how can they be same? Or you can do one more thing, but okay. Think what you can do, okay? So simply what you can do, you can just write it here, IB. IB is IC by beta, I can write, right? So 5k by beta is 80 into IC. Yes or no? And 150 times IC also I can write. Then calculate IC, what it is coming. I need IC, right? So 5,000 by 80, how much it is coming? 62.5 plus 150. So around 212.5 IC equal to 9.3. That is what it is coming. So 212.5 IC equal to 9.3. So what is IC? It is coming as 0.0437 amps. So if IC is known now, this is IC. So what is, and IC is known means IE is also known, because IC and IE are almost same. So similarly IE is also known, right? So then 0 plus IE times 150 will give me V0. Or V0 is nothing but 0.0437 times 150. How much is it coming? 6.56 volts, right? Any doubt? I just applied KVL and used this relation IC equal to beta IB. Beta was 80. So I converted IB into IC. Why IC? Because IC and IE are same, and once I know IE, I can find V0. Hope you are clear with this, right? So let us go to the next problem.
Sir, I have one doubt, sir. Sir, can you go back previous slide, sir? Here, IB equal to 10 minus 0.7 by 5 kilo ohm. Is it right, sir?
Yes, it is right. You
now,
just put it in here. And
yes, 1 minute, sir. I have one more relation, sir. We have one more relation. IC equal to beta into IB.
Yes.
Here, can you substitute IB value in this equation directly? We will get IC, sir. Why we go for this KVL and
yes, 10 minus 0.7
by 5
by 5 is IB, right?
10 minus 0.7 by 5K, 1.86 milliamps, sir, IB.
So 1.86 milliamps you got, right?
Yes, sir. Now,
then
from the given data, beta value is 80, sir.
Okay.
Now, 80 into 1.86, we got 148.8 milliamps, IC.
Okay.
Is it right, sir? The procedure.
See, what is happening? The procedure, what is there? You are doing 10 minus 0.7 by 5, okay?
Yes, sir.
10 minus 0.7 by 5 is what? IB. But this relation, IC by IB is beta. It gives us IC max.
Okay, sir.
Not IC. IC max is beta times IB.
Okay, sir.
And IC max is beta times IB means in the active zone operation. Now, what we did not calculate IC max. We calculated IC.
Okay, got it, sir.
Just based on the, so why we calculated IC? In order to calculate IC, you must use the KVL loop, the complete loop, which has also these biasing registers. Because if you only use 10 minus 0.7 by 5, you are only calculating IB. But I told you that IC is not only dependent on IB, but also somewhat dependent on VCE. Hope you remember what I told you. IC and IB are related, agreed. That when IB increases, IC increases. Mostly dependent on IB only, but not completely. It also depends on the emitter voltage. And since the emitter voltage here is somewhat different, you are overruling that, which you should not. So how to include that in the calculation and find out the actual IC? By this method. Why this method? Because this method completely calculates the network currents based on the biasing register. Biasing registers are very important. It can completely change the currents. And once you take into consideration this biasing register, you see that IC value reduces. You just calculated IC, you got a large value, 10 minus 0.7 by 5 into 80. got a large value, right? So that was the maximum IC value. But our device is not operating in that region. It is operating slightly lower, at a lower IC. Why? Because of the transfer characteristics here. It was having some small slope and with a small VCE. Why? Because your emitter is not zero. You see here. Emitter is it zero? No. Emitter is sitting at 6 volts. Yes or no? So VCE is slightly lower and that impacts the IC. Hope you understand.
Yes, sir. Thank you, sir.
This term was important and necessary to get introduced in the KVL equation to calculate actual IC. But you will again tell me that I am using IC equal to beta IB. Yes, but I am also using the emitter voltage IC. So just to make you understand what is happening, your IC and IE are correlated. And that's why calculating the complete biasing resistance included network is important. You should completely include the maybe what I can say, the completely the network and not directly do that. Wherever you see the KVL network, you should actually include that. Hope you understand what I am trying to tell. Otherwise, always it will come same. How can it come always same? If you change the emitter voltage, you change this 150 ohm, okay, hope you understand. Then emitter voltage will be different. And how can IC not change if VCE is changing? Because it has some impact, right? We saw in the relation. VCE impacts IC. Not much, but to some extent. You are getting, I am saying, right? That's why. So 10 minus 0.7 by 5 into that 80 will not make you see the complete picture. You are losing something. And that's what is the explanation. You also need to include the emitter into the calculation. Either use KVL or use KCL, but you need to use completely. Then only you can calculate. See, applying KCL here will give you only IC equal to I because IB is almost 0. But for that IB, what is IC? You cannot directly just comment using the gain relation. You can comment, but you need to include in the KVL relation. Right? So always remember that IC by IB is not beta, but IC max by IB is beta. You can use this relation with including bias resistance. That gives you the complete picture of the loop. Otherwise, the network equation is not correct. So that means that IC should be less than beta IB. Right? IC max is beta IB. But how much? That is decided by the network. Hope you get me. Right? There's not a direct relationship. Don't just blindly use it. Okay? So transistor is in active mode and this is just the network that it was 4 volts initially and now it is 8 volts. Then you see what will be the variation in RC. Now I told you, seeing the VCE, if you only change this voltage, then IC will change. But if you don't change VBE or VCE, can IC change? Right? If you don't change VBE, VBE is not changing here, right? You are not changing RB, so VBE is not changing. This is 10 volts, RB is same, so VBE is also same, and VCE is also same. Almost, right? So assume IC does not change, right? So 10 minus VC by RC old is nothing but 10 minus VC old and DC new by RC new. Current is same, right? Why current same again? Because base emitter is not changed. So I told you VCE has a very less impact on IC, but VBE has a larger impact, exponential relation. So if VBE is not changing, IC almost same. You can assume that. So using this relation, you can just calculate VCE old is 4 volts and VCE new is 8 volts. Just plug in 6 by RC old is nothing but 2 by RC new, and replacing the ratio RC new by old, how much? 1/3, right? Just basic. That just to make you understand that VBE, if it is same, just remember the characteristics. For a same VBE, for particular IB, VCE does not have a very huge impact on IC. So for the calculation, very quick calculations, you can assume almost IC is same, right? Because the bias resistor is not getting changed very high. And that is the VBE is almost same, that's why IC is same. And you can equate and get the new value of bias resistor. Hope you understand. And just this is one problem. So for you, just in the homework, you can use and calculate beta. Similar problem, right? So I give it to you as a homework. You just calculate and see what is beta is coming. Almost same problem, right? You can assume VBE, and from there you can calculate the currents and write the beta. Hope you understand, right? So beta will come in this problem to be 90, right? Just check. So just for convenience, I am writing emitter current is nothing but 10 minus 7 by 1. Okay. 3 milliamps. So IE, right? And from here you can calculate VC. Collector current you can calculate. Because this is 6.3 and this is 7, right? So 6.3 and how much is this? Because this is, I hope you understand, this is a what? PNP transistor, right? So just flip. So that's why there is a drop of 0.7. In which direction? Then obviously the current flow direction, right? So drop here. So 6.3 is just a PNP transistor. And then 6.3 drop is happening. So 6.3 voltage we know. And this is 0 volts here. So accordingly you can calculate the currents and can see. So what is VC? Can you tell me? This one, right? This is 10 volts and this is 7 volts. So accordingly you can calculate what is IC, right? And just check IC by IB to get beta. Yes, clear? I think this will be IE and this will be IC because this is the base, I think. And this is collector. Yes, I think this is right. Yeah, so then you can calculate IC by IB and get beta, right? So beta will come approximately to be 90, right? So IE is nothing but 10 minus 7 by 1, because this is PNP, right? So please be careful. PNP transistor, and this side is the emitter side. So okay, everything is inverted. So IE is known, 3 milliamps. Then we collector voltage, you can just calculate collector voltage. Okay, 3 times 1, which is nothing but 3 volts. You understand why it is 3? This current I am telling. Just I am assuming, okay, that IC and IE are almost same. So IC is also 3 milliamps, and 3 into 1 is nothing but 3 millivolts, right? Sorry, 3 milli and kilo, so 3 volts VC. So milli and kilo, yes. So VC is 3 volts. And accordingly, you can calculate IC. IC is 3 milliamps, and IB you can calculate, and just IB is IE equal to 1 plus beta times IB. So why I this? Because IE and IB will just give IC. So you form the KCL. IE plus IB is IC, and IC is beta IB. Sorry, the current flow in a PNP transistor, if you see, IE is like this, but IB will be like this, because from positive to negative, right? Like this. This is base current in this direction. So what happens? IE and then IB will be like this. Okay. So it will like this, huh? Okay. So what will be the KVL equation? Because you need to understand which is the direction of flow of current. So what is the direction of flow of current? Because current is flowing in this direction, right? So IC is in this direction, and IE is also in this direction. But which direction is IB? That you need to understand. So obviously into the N lead, this junction is forward biased, right? So current will flow out from in a NPN. What you do? The current flows out of P and comes into N. Same here, the forward bias, like this it will happen. So IE plus IB, okay, just try to form. What will it come? Just let me draw it clearly, okay. So this terminal, let me draw it in a inverted way. So this is what it is, a P N P, because that why I am getting confused, right? So this is the collector, this is the base, and this is the emitter. Now what I know, I need to forward bias the base emitter junction, and I need to reverse bias the collector and base junction. So I reverse bias with obviously some resistances. Now what will be the direction of flow of current? Current will be like this, out of the collector into the emitter. And current will be like this. Now you write the KCL equations, sorry. So IE minus IB is nothing but IC. So what you can write as the relation, IC is nothing but beta IB, IB plus beta IB is nothing but IE, which is nothing but 1 plus beta times IB. And that's why we have a name that IE by IB is known as alpha. Sorry. IE by, not in a, so you just write that IE equal to 1 plus beta IB. Not alpha, okay? Alpha is this. So if you go back, so alpha is IC by IE, which is less than 1. So this is okay. IE is 1 plus beta IE. You only remember this, and you can also derive. Okay, so that was it. You can just derive, and then beta was how much you can just calculate that. IB you can calculate. Yes, 3 volts, you know that it is collector voltage, and this 6.3. So 6.3 minus 3 by 100 will give you base current, and accordingly you can calculate. Okay, you can just calculate this, and I will just leave it up to you. So basically we are diving into OPAMPs. I know you know already OPAMPs what they are. So just remember that OPAMP is a device where its input impedance is very high and output impedance is very low. Such kind of devices can be used as voltage amplifiers, good source for driving the loads. Because output impedance very low, that's why the loads don't get affected by the change in load current. The voltage remains stable. And also one more additional feature that it gives is the isolation. It is a good, because of the input impedance being infinite, the input and output are separated. So the isolation feature is also provided by the op-amp. So it is good for isolation as well as voltage amplification. So that's the two reasons why op-amps are used. So solve this numerical. I will only take 5 more minutes, right? Solve 2 problems and then we'll be off for the day. So first problem is a 1 minute problem. Then we just see another problem and we'll just conclude. So tell me the answer. So you know the op-amp has 2 inputs, inverting and non-inverting. And due to the input impedance being infinite and the gain being infinite and the output voltage being finite, what can I conclude? V0 by Vi. If this is finite, then del Vi should be almost 0, which means Va and Vb should almost be equal. If not, then let us see the characteristics of the op-amp. This is the differential voltage, this is the output voltage. You know that if the differential voltage is within a very small range, the amplification zone is there based on whether it is inverting or non-inverting. But if it crosses the threshold, obviously Vd is Va minus Vb, voltage at non-inverting and minus voltage at inverting end. If it crosses, if it becomes very high, then 0. It goes to plus Vset, which we don't actually draw. These are the 2 saturation voltages. And if it goes too low, that means if Vb is much greater than Va, then we can understand that Vd is much less than 0, which drives it to minus Vset, which drives the output to minus Vset or plus Vset. Now you can understand this 1 volt VA is 1 volt in this problem, VB is 2 volts. So VA minus VB is less than 0, which is nothing but driving the op-amp into minus Vset. Because for the op-amp to function in the amplification zone, differential voltage should almost be 0. Otherwise, it cannot happen that the op-amp is providing the gain. Because if differential voltage is something other than 0, it cannot provide infinite gain. So then it drives the op-amp to saturation. That was the basic philosophy I wanted you to understand, that don't blindly just apply virtual short. This name is called virtual short, right? Virtual short. Don't apply blindly. You can apply virtual short, but you need to check always that V0 remains within plus minus Vset, because in no case can the voltage of the output cross plus minus Vset. In that case, if it is crossing, that means your input side is not in the amplification region. Your input is either driving the differential input, what you are giving, either driving the op-amp to the plus or the minus Vset. That is based on the output characteristics of the op-amp, based on the input voltage applied, input differential voltage applied. That is the rule how the op-amp functions and how it is designed. Now, based on this information, whatever we discussed, you just solve this simple problem, right? And then we'll be off for the day. So try to solve this problem. So what we can do, we can just apply, only remember one thing, that since the op-amp has input impedance infinite, so IP should be always 0. Why? Input impedance infinite. And IN should be what? Yes, IN should be IN should be 0, because the input impedance of the op-amp is infinite and it does not accept currents into any of the ports due to the input impedance being infinite. So now let us talk about something about the voltage. Let us apply virtual short. Vp is equal to Vn, because the op-amp needs to be thought operating in the amplification zone. And first you assume that the op-amp is not operating in saturation and try to find the output voltage. If output voltage mod less than Vset, then it is okay. Let us see. First apply virtual short, and now see Vp equal to Vn. Good. Now let's see what is Vp. So what should Vp be if Ip is 0? Vp should be what if Ip is 0 in this path? 3 volt minus Ip into 10 equal to 3 volt, which is nothing but Vp. So Vn is also 3 volts because Vp equal to Vn. So Vn is 3 volts. If Vn is 3 volts, this point is sitting at 3 volts. So can you tell me what is V0? And can you also tell me what is I? Based on this information that this link point is sitting at, or this node is sitting at 3 volts. Easy, right? Now just apply the KVL. Because current does not reverse flow, this current is 0. So only you have a loop where you have a V0, 3K, 3 volts, and then this is 1K, and then this is 0. Apply KVL. V0 minus 3 plus 1 kilo times some current, because this current flows directly down, because it cannot flow here because input does not accept any current. So V0 minus complete I times 3 plus 1K is nothing but 0. And we also know that I times 1K is 3 volts, where I is nothing but 3 milliamps. Plug it in here. V0 minus 4K times 3 milliamps equal to 0. So V0 is nothing but 12 volts. Hope you get it, okay? And 12 volts is less than 15. So op-amp operates in amplification stage. Op-amp not saturated, right? Op-amp not saturated because output is well within the threshold, and then only we can apply virtual short. Only if op-amp not saturated. This works only if op-amp not saturated. Hope you understand, right? Any doubts? So you can apply this concept and solve, right? Most of the problems will be done by this concept. Any doubts, you can let me know, or else we can close the session, right? Because we are already out of time. So if there are no doubts, then we can close the session, right?
No doubt.
Okay. Then we can close the session because op-amps you can just be able to solve. Just check the terminals and accordingly you apply KVL or KCL. In most of the problems, virtual short will work and you will find that output voltage remains within the plus VCC or minus VCC. And if nothing is specified, then you can apply VCC to be, you can assume this VCC, what we'll call, or minus VCC to be 15 volts. And if V0 after the problem solving is coming within 15 volts, then obviously your assumption that VP and VN was same because the assumption of virtual short works well. Otherwise, you can have to apply. You can, if you see, for in such some cases, if V0 is coming equal to 20 volts, this is not possible. Then you have to assume V0 is 15 volts only. And using this information, you need to calculate VP and VN separately. Because in that case, VP and VN are for sure different. That's why the differential voltage was coming and driving the op-amp to saturation. That is the only concept. So in this case, V0 is not 12, not 15, but V0 is 12 volts. Okay. Hope you understand, right? We can close the session, right? If you have no doubts. So try, and if you have any doubts, please let me know in the group, right? So we can close the session, right?
Okay, sir.
Okay, thank you.